Hi, it's Professor Dickerson again. So this tutorial is going to help you use a script in JMP to study the sampling distribution of the mean. Now, what is that all about? So the sampling distribution of the mean is basically showing that, for any population, there are lots of different samples that could be collected. And each of those different samples would have a sample mean that goes along with it. So the sampling distribution of the mean is the distribution of all those sample means that would be possible if we sample from a population and if we stick to a specific sample size. Okay. So for this, you'll need to already have the CARS 2015 data set open. So I have it already. And then you'll also need this approximate sampling distribution JMP script. So if you haven't already, download that and then open it up. Okay, so what we're going to do is indicate that we want to use the CARS data. We don't want to use this built-in demo. So up here where it says population shape, pull down there and select My Data. All right, and we're going to be choosing from the CARS data, so pick that. And we need to decide what it is that we're going to look at. So I am going to pick how about the heights? We saw those a little while ago. So assign that as X and press OK. We can create a histogram of that population down here. So this is just a histogram of the heights. We actually saw that in the earlier tutorials when we were just making histograms. All right, so clearly the heights have a non-normal distribution, perhaps bimodal, bimodal because there are certain vehicle classes, like cars tend to be shorter, whereas SUVs tend to be taller. And the population mean is here, so that is mu. Remember, a population mean is symbolized mu. So mu is 61.42. And below that is the standard deviation. And again, if we're talking about the whole population, that would be sigma. So sigma is 6.6. All right, so in the population, if we're talking about single vehicles and how are they different from each other, the typical distance from the mean is 6.6 inches. Okay. So that's talking about individuals, that is, single vehicles and plotting their heights. But with the sampling distribution, we're going to be drawing samples from this population. So I'm going to start with n equals 4. So I'm going to set the sample size to 4. And let's say at first, just to illustrate what's going on, we only choose one sample. Okay, so I'll keep that at 1. And I'll say draw samples. Now, if you're following along, don't be surprised. Your result up top should be different from mine. Because what JMP is doing is it's choosing 4 vehicles at random and then plotting their heights up in this top window. So, 1 vehicle, 2, 3, and 4. All right, so this is just one possible sample that could be selected. Yours is probably different, and someone else in the class, they're going to have still yet another different result. So for that particular sample, this is the sample mean, X bar. So the sample mean up here is 64.5. So on this lower plot, we've got a rectangle above 64.5. If we do it again, say draw additional samples again, the top window changes, reflecting that we have a new random sample with a new sample mean. So the second time I did this, I got 57.25. So it's going to be represented down here. Okay, so due to the random nature of selecting vehicles, our results are going to vary. So that's called sampling variability. And the idea with the sampling distribution of the mean is to try to get a handle on, well, how much are these sample means going to vary? Are they going to be fairly consistent, or will they be quite different? So we can speed this up and choose a very large number of samples. For instance, 1,000. Let's draw additional samples now. Okay, so after a little bit of hesitation, we'll see that this fills in a lot, reflecting that we now have 1,000 different sample means that are being plotted. Okay, so you can ignore the top for now because this one sample isn't anything special. It's just one of many that could be selected. But down below, we have kind of compiled the results from 1,002, in this case, samples. So these are the sample means from all those different samples. Now, the properties of the sampling distribution for the mean, the first one says that the mean of the population, so that is, remember, this guy here had a mean of 61.42. Well, that should be the same mean as for the sampling distribution. Okay, so how did we do on our simulation? Well, this says 61.5352. Okay, so they're pretty close, 61.4, 61.5. They do vary a little bit because I've done 1,002 samples, which is a lot, but there are still a lot of samples that I have not collected. So just due to the chance of who's there and who's not, we can expect a little bit of fluctuation. If we exhausted every single possible sample, and there'd probably be billions or trillions of them, then we would expect our results to match exactly. Okay, so that's the first property. The second property of the sampling distribution says that the standard deviation should be approximately equal to sigma over the square root of n. Okay, so sigma would be how widely distributed was the population to begin with. So 6.6 inches was the standard deviation originally. Well, we'd take that and divide it by the square root of the sample size. So what was our sample size? Well, that's that we were choosing 4 cars each time. And I chose 4 because it's a nice, you can take the square root easily. So the square root of 4 would be 2. So we'd be taking sigma, 6.6, and dividing by 2, which would give 3.3. So in theory, the standard deviation down here should be about 3.3. How'd we do? Well, in our table here, it says, well, actually, we got 3.17. Okay, so it was 3 point something. We're kind of close. And 2 reasons that it's not an exact match. Well, property number 2 is approximate, the wavy equal sign. And then also, same as with property 1, well, we didn't exhaust all possible samples. This is just 1,002. If we did more, our results are going to fluctuate slightly. All right, the third and final property of sampling distributions has to do with their shape. And if we look at the population, remember, this was very non-normal, bimodal and this long tail to the right. But the sampling distribution, particularly if you kind of think about smoothing these bars slightly, it looks a whole lot more normal. It's not quite there yet, but it doesn't look bimodal anymore like the population did. Okay, let's reset and up the sample size. So another one with a nice square root is 9. Let's change that to 9. And let's skip right to 1,000 samples. Okay, now look at that. It's looking a lot more bell-shaped. So we can see the central limit theorem in action here, showing that, well, even though the population was bimodal, as our sample size gets larger and larger, the sampling distribution will tend to resemble a bell curve. Okay? So there we go, and we finished within our 10 minutes. Way to go, us. I'll see you later.